share. You guys see that?
Yep.
Yes, we do.
Yeah.
Excellent.
Survey report. All right, cool. Thank you.
Excellent. Showtime. All right, welcome everybody. Oh, I forgot to put my mask on. I'm sorry.
Safe
I
video,
want you to
very
be able to
important.
see this mask. It's not astronomically accurate, for the record. I don't think those planets and stars are actually situated in the sky that way, but that's been the mask I've been wearing. Let's see, Joe Lamb is here. Thanks for joining us. I'm delighted to have Ed Guinan here, and I'm looking forward to his presentation on Betelgeuse. That's the only time I'm going to say it because I don't like what happens when you say it 3 times. So we'll move right in. Someday we're going to do this live again, and I'll get to do some sort of presentation. But I don't like to take up the time when we're doing it via Zoom. I'm delighted that all of you have power. Those of you who do, those of you who don't and are still here, I'm seriously impressed. I'm going to ask you when Ed starts his presentation that everybody shuts off their audio and also shuts off their video so everybody's got clean bandwidth going through in the meeting. I'm looking at my list of who I got to throw the meeting to, and the first one would be Brian. Brian Lee, you got anything to tell us?
We have no new members this month, but you were telling me about a possible new member, so I look forward to hearing from that person.
Excellent, excellent. All right, and next is Lewis. I'm going through in my mind's eye who's sitting where at the Radnor room, so that would mean Lewis is next.
Well, I'm pretty far from Radnor, about 8 or 9 miles, so I'm not sitting real close to it. But so far, I haven't embezzled all your money, and I can happily report that I just got our latest statement. We made 25 cents in interest.
Oh boy!
So really, really excellent job on us, and nothing much to report.
Very good. I guess you and I will attack that list of, I think it's down to under 24 members.
Well, there's 141 members right now, and I have called or reached out to everyone in my original list, which was 25 people. So
great.
So, but we certainly could call them again.
Okay.
It is. And thank you all, by the way, for your membership money. It helps us do programs, helps us do things like purchase Zoom. It helps us do outreach and other activities during the year. So thank you.
And speaking of Zoom, I noticed they have a huge sale on a full year, and it looks like we'll be doing this probably at least through July. So it may make sense to switch this to a full year. We can talk about that. All right, who's next? I think Jen said she wasn't going to be on, and I don't see her.
That's correct.
So I'm going to throw it to Nate to talk about Cherry Springs. Nate has wandered away from his computer, I'm guessing, or forgotten to unmute himself.
His wife heard him say that he blames her for everything. So
right.
He's
all right. With Nate away, Andrew, why don't you do your thing, and we'll check back to Nate after the observation report.
Actually, guys, I'm here. I'm sorry about that. You caught me in the middle of running chores. I have been tasked with finding thermometers, so pray for me because they're like non-existent. Cherry Springs. Chester County is basically, Astronomical Society has basically said that they're interested in doing it. They want to do it during the week. Off the top of my head, I'm blanking on which one it is, but it's in July, middle of July, around the new moon. And so the big question is what's going to happen with the pandemic. So that's the elephant in the room. So at this point, I mean, yes, put it in your calendar. I'll try and send out, the dates involved after I get home. But for now, put it in your calendar, see if you can make plans around it. But again, we're in the midst of a pandemic. Thanks.
And people tend, if you stay tuned on the listserv, people tend to make their plans known there. Some have discussed, perhaps because it's such a commitment, going 5 hours up to Cherry Springs, possibly doing something at Blue Mountain, which we'll coordinate. The new moon is actually about 5 days after Chester's talking about taking the trip to Cherry Springs. I think they're talking like Tuesday or Wednesday to Friday, and the optimal viewing is actually more like Friday or Saturday through Monday or Tuesday. So folks may want to make different plans, but we'll see what happens as it gets closer. I know there's pressure. I know that the state is opening all of the recreation areas in the near future, and that Potter County is probably already in the green zone now.
Yes, it is.
Yeah. So at least that should not, barring another surge or spike in cases, that shouldn't be a problem. But when we get closer, there'll be more chatter about it. And we have a July meeting. We can talk about it again then.
What's the status?
Exactly.
What's the status for camping?
They're open. Cherry Springs is open.
Yeah, Cherry Springs is open for camping. I don't recall what they've said about the toilet, but I presume that's okay. Can't speak for the showers at
Lyman Run.
Lyman's Run. Yeah, can't speak for that.
Yeah, I was up that way about 2 weeks ago, and no problems at all. Camping, doing whatever you want to do. Rules are really relaxed up there. There's really nothing like going, there's so few people up there that it's the only thing that they were doing was complying with state regulations on beaches and maybe boat rentals, but otherwise, yeah, it's just like normal. Bathrooms, just use a lot of hand sanitizer, you're good.
Okay.
The dates
Now,
are
what I will say is that if we're going to do this, I really need to stress the importance of masks, social distancing, all that kind of stuff. That's going to be critical up there.
And don't share eyepieces.
Here's what we did.
Yeah.
When we went camping, we brought hand sanitizer, and you would just sanitize your hands before and after going to the bathroom, because that's really the touch point. Now, if you're talking to someone or whatnot, just wear a mask. But otherwise, like, the bathroom's the area where you can't negotiate touching things.
Mm-hmm.
So,
Right.
July 13 to 17th are the dates.
Right.
Yeah, but again, those are the new moon is actually the 20th.
Yeah, we picked that to avoid the crowds in the weekend.
Okay.
That's why we picked it, to
But-
avoid that. So I picked it.
Okay. All right. But you didn't want to avoid the moon, apparently.
Well, it doesn't rise until about 1 a.m. and most of us don't stay up in our club. Don't stay up much past 1 a.m. So
Okay.
if you come the later part of that, then you'll have a later rise yet. So
Yeah, but you really don't get darkness till 10 o'clock, do you?
yeah, about that. But it's probably an hour till the moon really gets up high enough to matter.
Mhm.
So it seemed the best compromise between being there on a weekend, which we didn't want to do, and avoiding the moon. So,
Okay.
and doing it in July allows us to have August as a backup.
Right. And if you don't want to be there on the weekend, then I guess that makes sense.
We don't want to be in there on the weekend.
Okay.
No.
when's the Woodman's show?
That's usually at the end of July, or I think, or early August.
Yeah. And they don't usually schedule that around the new moon anyway.
Right.
So we should be all right.
Last year, they kicked us out before the new moon went away for that show in July.
Yeah.
So they did actually take away some nights from us.
Mm-hmm.
The light Nazi finally kicked us out.
Yeah.
The
He
Woodsman
apparently has a chainsaw too.
The Woodsman show is canceled this year.
That's what I thought. I thought I saw that on their site.
Yeah. It was supposed to be August 1st and 2nd, but they canceled it for 2020.
All right. Let me just see if I see some stuff in the chat. No questions. Okay.
I have one thing I realize I can give the presentation. Jan had a 2-slide deck that she sent around.
Go ahead.
Right.
Hit us with it.
Yeah, hold on a second. Let me just go for the screen.
Jeremy, turn on his share screen, Jer.
Yeah,
You should be good.
there you go. Do you guys see that now?
Yes.
Yeah.
So anyway, there's a new website link. Ask an astronomer an astronomy question. Our very own Al Lamperti is here to help. It can be accessed via the DVAA website, and it's public, but also a cool thing for everyone. And thank you to all the members who helped organize that. And the next thing is, understanding
Thanos.
the universe and finding our place within it. So that's still on for June 13th, Mike?
Yes, it is. Saturday the 13th
You
from
want
2
to
to
give a plug?
3:30. No, it's from 2 to 3:30, and I'm doing it through a Zoom Pro account that I purchased. And I'll send everybody a link. Whoever registers on the website, that's who I'll send the link to.
Very cool. Well, that's it for outreach. We're not reaching out very far, but at least somewhat. Thank you all. So back to you.
Okay, Hitch, you're up.
Okay. Yes, I realized halfway through that I didn't switch my name back to after my meeting with my hockey team, and
Hey, I think
it wasn't appropriate for this time.
It's cool.
Anyway, so my name is Andrew Hitchner. I'm the observing chair for DVAA, and this is the observing report for June 2020. And we might not be doing a lot of observing right now, given the current situation, but I was thinking, we're talking about going back to Cherry Springs and all, and some of you might be looking towards like local areas that you can start going back to and all. And I thought, well, I could do something about what's up in the June sky, but actually, you probably haven't gotten the equipment out in a while, and it's probably been sitting there, and you're still home for most of the time, might not have a lot to do. So what better thing to talk about than equipment maintenance? Because now would be a great time. And there we have a picture of the intern or postdoc at the observatory climbing to the top, scrubbing off that little speck of dust. So, but it won't be that hard for you. So I want to discuss equipment maintenance for telescopes, reflectors, and refractors. They do require different maintenance. I wanted to discuss some eyepieces, a little bit of mount maintenance, and even camera maintenance if you do astrophotography. But a few disclaimers to get out of the way. Do not clean something just for the sake of cleaning. So mild to moderate dust is okay, really. But you don't really want to clean every single speck of dust off as soon as a little tiny dust particle lands, because every single time you clean, it does wear away a little bit of the optical coating on these optics. So judge what you have, and you can consult us. Of course, there's the new link on the there's a new link on the website if you need help, but do not clean something just because you're bored and you think it might be the right thing to do. Like, actually assess your instruments and see if it's time to clean it. Also, always consult user manuals before cleaning for advice on how to clean things, whether or not you can clean it. Some things do need to be sent out to the factories to be cleaned, and especially if you want to dismantle everything. So those 2 points are so that I don't get any angry emails after this, because I told you to go clean it and take apart your telescope and now you can't get it back together. So always consult manuals. So first I want to talk about refractor lens cleaning. And really this applies to any kind of lens cleaning, whether it's for eyepieces, filters, even camera lenses or so. So the reason that we clean lenses is because dust can reduce the amount of gathered light by the telescope. And it also increases internal scattering. It applies more to mirrors or reflector telescopes, but that's why we need to clean the mirrors and lenses. So small to moderate amount of dust is okay. Now, if you look at your lens and there is a nice sheet of dust on top of it, then you might want to consider cleaning. So if it's just dust, that's good. That's easier to remove than fingerprints or so. So to remove dust, you can use compressed air. Some people like to use like bulbs that you can buy from lens cleaning kits. They do apply a little bit less pressure than the compressed air cans, although I've seen arguments for both. So just go what feels right, do your research. And then after you use the air to brush off all the dust, then follow by a very soft, fine brush, or like a camel hair brush that you would buy for like art supplies or something. Those are very soft and that they won't scratch while you're removing the dust from the lens. Now, after you remove the dust, if you see visible stains, then you need to dig a little deeper and actually apply some solutions to remove them. So you can make some cleaning solutions at home. And I didn't link anything specific. There's a lot of links out there, a lot of different solutions that you can make. A quick Google search will get you a good solution to make. Or you can buy a lens cleaning kit. I have a lens cleaning kit from Orion that I use for my eyepieces and my camera lenses, actually, and it works really well. And it comes with an instruction manual and all. But basically, you're going to take this cleaning solution and then you're going to dampen a piece of lens tissue, and then you're going to blot the lens. So don't move too much around or anything at first. Just kind of blot the areas where there's a fingerprint, because we don't want to scrape the fingerprint or scrape the lens at all. And then after that, you can go in little tiny circles to remove any of the stubborn areas. So this is the general procedure. This isn't all of it. It doesn't cover all of the nuances, so definitely do some more research, but it's actually not that hard. And the same procedure applies for both eyepieces and filters. So for reflector lens cleaning or mirror cleaning, actually, sorry, this shouldn't be lenses, it should be reflector mirror cleaning. First, you're going to want to remove the mirror, the primary mirror, or the secondary, and definitely follow the user manual for that. Each telescope has a slightly different way of doing it. And first, you're going to remove the dust the same way with compressed air. I've actually seen that they don't recommend any brushing at this step because the mirror surfaces are much more sensitive to scratching than lens surfaces. That aluminum coating on your mirror is very, very thin. So you need to be very careful when removing the dust. Then you're going to inspect the scratches for holes. And you can do this by putting your lens right on the workbench that you're on and then putting a light right above your lens. And you should be able to see a blue image of the lens that kind of appears below, or sorry, the mirror, that kind of appears below the mirror itself. And you'll be able to make out any scratches or holes in the coating by holes that don't move with the image of the mirror. Now, if you see any scratches or holes, make your own assessment. Unfortunately, there's nothing really that you can do to fill in those holes rather than sending it out to the manufacturer. Or if you ground the mirror yourself, you might know a little more. I haven't ground a mirror myself. But do your own inspection, your own judgment, and don't be afraid to call the manufacturer too if you have any questions about whether or not you need to send it out. But most places like Orion and Celestron will recoat mirrors for you. And then you're going to basically clean the mirror in the sink. So you're going to let some warm water gently run over the surface, hopefully at an angle. And then you're going to build up a layer of water and then a little bit of dish soap and then submerge the mirror in the dish soap and then kind of move it around in the water to hopefully get off any of the stubborn dirt or grit that is on the mirror, any fingerprints. And then still working under the water, you can take a surgical cloth to gently remove any of the stains from under the water. So when you're happy with that, then you could let it dry at an angle. You should probably rinse it off again at an angle with some warm water, and then let it dry at an angle either in the sink or you can let it dry on a cloth. I saw one article that I read, they propped it up with pillows on their bed or something. Make sure the cat doesn't jump up or something. But make sure it dries at an angle so that all the water continues to fall off of the mirror. So other than cleaning, what's some other things that you can do to maintain your telescope? Well, one thing is collimation. So collimation is the effect where if you look at a star that should be round, if your telescope isn't properly collimated or aligned correctly, that round star could now be an oval shaped or an ellipse shape. So for reflectors, you can use handy tools for this, a collimation cap, or I use a laser collimator in my reflector. They're very easy to use, and basically you're going to look at the laser shining up into the collimator and try and align it to a bullseye. And you're going to do that by adjusting the primary mirror with knobs on the back of the mirror. And you can look at your manual to see how to do this. So all reflectors should be able to do this. You can also do the secondary. I've never had to do the secondary, although you can do it. My Orion, you can take a little screwdriver and then you can undo or tighten some of the screws behind the secondary to move that. Now, this should be done every single time you set up. However, if you've never done it before, or you might think that you need some practice because you haven't been out in a while, definitely set it up and see what you can do. If it's really bad, then take the time in the daytime and inside to take your time with it and try and get things back in order. Now, refractors, it's a little bit of a different story. So refractors are collimated in the factory, and the lenses can be adjusted. So my Explorer Scientific, I can take in a wrench and make slight adjustments to the primary optic. However, it's really not recommended. And if you take out your refractor and you see that you do have some collimation issues, you can always send it out to the factory. And I can't speak for all, but I know Explorer Scientific will collimate it for free. You just need to pay the shipping costs and all. And finder scope alignment. So it's very easy to set your telescope up in the day, point it to a distant object very far away, and then just center it in your scope, and then use the adjustment screws on the finder scope to get that right in the middle of the bullseye, in the middle of the finder scope. Again, this is something that you should probably do every single time you set up, but if you haven't done it in a while, or you knew that last time you got frustrated and because it was so far off and just gave up with it, take the time to practice during the day and get it right. So what can you do for mounts? Well, there's not too much you can do for mounts. For Dobsonian mounts, you can check the motion of the mount, maybe pull it, move the telescope up and down. If there's a little bit of resistance, you can buff the Teflon pads with some car wax, or you can just straight up replace them if you made them out yourself. Also check the rigidity of the mount. So my Orion, the mount's really good, but it's kind of just particle board. And sometimes I do need to go in there and I do need to tighten the screws a little bit just because bringing it in and out of the car, setting it up, got a little wobbly. For tripod mounts, you can oil the gears for smoother motion, and you can adjust the weight of the counterweights or the telescope, adjust the balance. If you are going to disassemble anything, make sure you check the manual to see how you can properly disassemble things, and even if you can, disassemble them. And I know this isn't part of the mount, but you can always oil your focuser too if you need a little bit of smoother movement around that. So camera maintenance. Cameras, really, there's not too much you can do, but you can clean the sensor in your camera. And the best way to know if you need to do this is take a flat field. And actually, this is a great time if you've never taken a flat field. This is a great time to do it while we've had all this cloudy weather and while we're not really getting out into the field. So a flat field will basically show you all of the imperfections in your sensor. And you're going to take an image of a white surface that is evenly illuminated. And then you know that any dim areas or any blotches are due to fingerprints or dust or anything. If you do this with a telescope, if you have an astronomical CCD, you'll have to do it through the telescope. There's lots of ways to do that. If you have a CC or a DSLR, you can always just attach a clean camera lens and take an image of your monitor. As long as your field of view is less than how big your monitor is, you can always show a bright white screen in your monitor and then take a few pictures of your monitor to get your flat field. And actually, if you have Adobe Lightroom, you can use the spot finder and it will point out all of the quote unquote spots in your image. With a flat field, that's going to be the dust. So a really handy way to figure out where the dust is. So to actually clean your sensor, it's really a lot like lens cleaning. So with DSLRs and astronomical CCDs, the sensor itself is not exposed to air. It's in a vacuum sealed chamber, and then there's a plate of clear glass on top of that. So it's okay to touch it. I wouldn't touch it, but it's okay to clean it directly. And you're basically just cleaning the clear window above it, a lens cleaning. Now, if you do have a DSLR, you're going to need to lock the mirror. You can do that through the menu of your DSLR. And I would just hold the camera upside down, brush off any dust very lightly with a fine brush. And then you can go ahead and use any solutions if you need to. And just a note there, if you do use a DSLR, if there is motion stabilization, I know you don't use it for astronomical imaging, but if you ever take this camera off and you want to do it for any normal photography, you're not going to want to ruin the motion stabilization, and that can be ruined while you're cleaning. So take note. if you have that. Other than sensor cleaning, update all your drivers, update all the software that you use, everything that you use to drive your CCD, everything that you use to take images. Make sure that's all up to date. It's always a good thing to do. And you go through your image folders. Maybe you can organize some things. Maybe you can delete images that didn't work out so well. Just go through and see what you can do. What are some other maintenance, some odds and ends? Well, you go through your cases, maybe clean out cases of dust or whatnot. Go through your batteries, make sure everything is charged. And those batteries that you can recharge, make sure that they're holding a charge. If they're leaking charge, maybe it's time to get a new one. And any batteries that you can chain the batteries in and out of, make sure it has new batteries so that you're ready to go out there. And just organize things. Just go through your books and your logs, throw out old logs, update new logs. I keep a nice crate of books that I always bring along. Maybe I'll go through those. Eyepiece cases, make sure they're all organized, in the dark. Maybe you put in another eyepiece where another one should have gone, go through, make sure they're all in the right place. Any telescope accessories such as dew rings or anything that you might have. And observing kits. I keep a little kit around so that when it's time to go observing, I can just grab it, and it has things like a water bottle, it has some snacks in there, it has hand warmers, foot warmers, some extra socks or whatever. And maybe go through that and update that, see if it needs anything. All right, and that's all I have.
Thanks, Andrew. Appreciate it. The thought of taking my primary mirror out of my Newtonian, my Nexstar 8SE is not something I will do anytime in the near future unless I absolutely have to do it. But thank you.
It is nerve-wracking. But
yeah, I may need a sedative to do it. So, Jeremy, I've been looking forward to our guest tonight for a long time. Been reading all about him. Why don't you introduce Ed, and we'll get to the main act.
All right. Thanks very much, Harold. I just wanted to add something to Andrew's presentation. When you said using compressed air, you have to be really careful with the cans of compressed air because they have a liquid propellant inside. I've had that experience where some of that stuff comes out. So you really want to be careful.
Try and keep it parallel. You always want to keep it parallel so that the liquid, doesn't come out. Hurt you.
All right. So I'll start with a little preview of what's coming up next month. For our July meeting, we'll have John Sickle, who is a professor of music. Yes, you heard that right, a professor of music at Raritan Valley Community College in New Jersey. He's also an avid amateur astronomer, and he's going to be talking about music in space. Now you might say, well, you can't hear music in space because it's a vacuum, but of course you mean space movies. So Star Wars, Star Trek, 2001. How do they use music? Do they play major keys, minor keys? What historical music have they used? It's going to be a really interesting presentation. So I encourage you to tune into that on July 10th. This month, we have another speaker that we've been looking forward to for quite a while. I've been trying to get him for a little while, actually, on several different topics. Tonight's speaker is Ed Guinan, who is a professor of astronomy and astrophysics at Villanova University. So Ed actually got his start doing his undergraduate degree at Villanova and then did his PhD at the University of Pennsylvania. And since then, he's been basically involved in every field of astronomy with a tremendously wide range of research interests. This includes solar system astronomy, and he was involved in some of the observations of the rings of Neptune. He also looks at binary star systems, the sun and sun-like stars, variable stars, pulsating stars, searches for exoplanets, interstellar space travel. Another story you may have heard about recently is growing plants on Mars, in particular edible plants, and what the prospects are for doing that in Martian soil. He's also been very involved in developing international astronomy, including places like Iran and North Korea. So definitely very international astronomy. So Ed is regularly consulted by the media for a variety of projects he's involved in, including this work on Martian soil. But most recently, he's been in the news because of studies of brightness variations of the star Betelgeuse. So there have been a lot of stories about why is Betelgeuse getting dimmer? Is it getting ready to blow up? And I've been waiting to hear from Ed on this for a long time. So we're very pleased to have him here tonight. So I'll just remind you to please mute yourself and shut off your camera, unless you're asking a question or have something to add to this. So without further ado, I present Ed Guinan.
Great. Thank you for inviting me. So what we'll be talking about tonight, let me get my picture. Can you make my picture smaller? How do I do that? Oh, there's the PowerPoint. Yeah. So we're talking about what's called the recent fainting of the bright red supergiant. Betelgeuse is a prelude to a supernova, which I knew. I don't know the PowerPoint. Yeah.
I'm not seeing the PowerPoint.
It's called the recent fainting of the bright. What's going on? Hello? I don't know. Can you hear me?
Yeah, I can hear you. Can you share the screen?
So I'm on. Okay. So I got interested in Betelgeuse in the 1980s, and at Villanova, we've been observing it since '81, and then we switched off to observe it with an amateur astronomer, Rick Wasatonic, Lehigh Valley, who has a little observatory in his backyard. So we've been doing this since I was a child. So let me just find there it is. These are the talking points, Betelgeuse or Betelgeuse. I'll tell you where the name came from. It's placed among the stars, physical properties and evolution, 200 years of observation, starting with Herschel, and the so-called Great Dimming, which happened just recently. And then we'll go into Betelgeuse as a core collapse supernova. That's a supernova where it produces an iron core. The iron core implodes. Neutron star, black holes produced, and then a shock wave runs out. And then I'll be comparing what Betelgeuse could look like in the future to some of the brightest supernova seen from Earth in the last 1,000 years.
Ed, your PowerPoint is not being displayed.
Why is that? Okay. Okay, what should I do? Share screen or what's the
yeah. Share screen.
Your video is also off.
Oh, really? Let me go back. What do I do? Turn off here?
Turn on video.
Turn on video. Right?
I don't even have that. It's not showing. Let me go back.
Down the bottom of the screen on the left-hand side.
No, it isn't there. All I see is my video.
I just sent you a request to start videos. See if you see that.
Okay. Let me go share. Let me get my glasses. We had it all set, ready to go.
But you just for a second, you had it. You're just showing the wrong screen.
Okay. I want to go back to, I don't even see Zoom here. Where is it? I'm on the wrong screen. So
that's a Zoom screen. Right now you're on your browser.
Okay, so let me do share screen.
Sure.
And now it's not there. We had the same problem before. It's not one of those icons, papers. It's what you get when you use someone else.
Wait, it said you started screen sharing. Now you were on your Zoom browser. So keep
Google
going.
browser, keep it going, right?
Okay, I don't have the Zoom commands.
But you seem to be cycling through your screens. We see them popping up.
Yeah, we see Google right now.
So I see PowerPoint down the bottom, Ed.
Yeah, I see it. Okay. Oh, okay.
There you go.
Success.
Okay, start my video. Oh no, is that true?
And just press F5. So
no, just press F5 to start the slides.
Okay, slideshow. See it from beginning.
Yeah, sure.
That's it.
Looks good. Thank you.
Okay. Does that work? Okay. Sorry about all that. Betelgeuse underwent from behaving, it was discovered 180 years ago and behaving kind of regularly. It did something unusual this year. It dimmed a lot. So this work was done with Richard Wasatonic at Villanova. He also is a member of the Lehigh Valley. These are the talking points, which I went over real fast. It's placed among the stars, physical properties and evolution, 100 years, 200 years of observations, the Great Dimming, as it's called. And Betelgeuse has a core collapse supernova. That's its ultimate fate. It is developing a carbon and oxygen and eventually an iron core. And then the iron core has nowhere to go. It implodes. Then we'll compare it to other bright supernova. And then we'll go back to some kind of interesting future prospects. So here's a picture of it. Betelgeuse taken from Hawaii. That's why you get stars right down to the horizon there. And you can see, you know, Betelgeuse and Bellatrix and Rigel and the belt stars and all that. And there's the Orion Nebula. And normally Betelgeuse is the second brightest. At one point, it may have been brighter than Rigel a couple hundred years ago, but now it's 2 or 3 times magnitudes fainter. Okay, there's the typical way of looking at it. You see Orion over here with his cloak, the golden fleece, and fighting the celestial bull. He got into trouble with some of the gods, and that forced him into these fights. Now, the original, the oldest constellation drawing is actually in Iran. It's in a book called Al-Sufi. Al-Sufi is a Persian astronomer. He wrote in 964. He wrote a book called The Places of Stars, the Fixed Stars. So this is kind of the original drawings. This is one that's copied from that, because I took it because it's color. And here you see Betelgeuse, and its actually real name is there. And there's Rigel down here, and the belt and sword and all that kind of stuff. And they always in these books, they always have how you would see it from the Earth, and how you would see it looking down on the Earth. That's one of these alien shows. Now, down in here, this is the problem. Betelgeuse, its actual name is Yad al-Jusa, and that's what the Iranians and Persians call it. And that's this here. And what happened is that in the Middle Ages, one of the letters got mistranslated. This Yad got mistranslated to be a B, and so that's where Betel comes from, Betelgeuse. So its actual name, I'm trying to get its actual name restored, Yad al-Jusa, but probably will never happen. So then we have Betelgeuse, Betelgeuse, you know, all these names. And in even German, there was a problem. So in German, it's Betelgeuse. And because this I here, they mistranslated a T for an I. So it became Betelgeuse. So it has problems with people messing up its spelling of its name. Here's a depiction of what you're more likely familiar with Orion fighting off the bull of heaven with the golden fleece and all that. And that's from Flamsteed. That's a copy. That's a Flamsteed page from this book, but someone has gone over it and painted it. That's worth $1,700. You can buy that online if you have money. And here's a picture of Betelgeuse, not Betelgeuse, the constellation Orion, showing the movement of the stars for 100,000 years. We're now at 50 AD. Now we're going to go back. You see that they stay about the same, the major stars. And that's because they're about the same distance. They're 600 to 700 light years away. These guys that are moving, that's our comparison star, are nearer. And this star over here is Pi Ori, which is a nearer star. It's only 30 light years away. So the things you see zooming across there are stars that are in the foreground. And you see Aldebaran creeping in to this side over here, because that's a nearer star too. But there is a slight movement. I mean, I did a paper in 2007 on Betelgeuse. We took its proper motion and radial velocity, and we kind of tracked it back to OB1 Ori right in here. And kind of, I mean, because there's too many uncertainties. We think it originated, it's a single star. Mostly all O and B stars, young stars are binaries or triples or in clusters. Betelgeuse does not have any companions. Rigel does, because we think it was kicked out of a binary star and ended up over here. It's traveling pretty fast. These stars here aren't moving very much. So that's another thing going on for it. It's a solitary star. This is a typical picture you see of the Orion area. And over here is what's interesting about Betelgeuse is the second largest angular diameter of stars in the sky. In this measurement, the angular diameter is 43 milliarcseconds. So in 1921, it was the first star to carry out interferometry, where they measured the diameter, and they measured the diameter close to that. And we're going to go back and see this again, but you see this is the Earth's orbit. In here, this is 1 AU, this is 5 AU. It almost goes out to Jupiter's orbit. This is taken with HST, so there's no seeing problems. You just have to eliminate the telescope. The instruments now can actually resolve this into 64 pieces. Oh, here comes my cat. This is, I didn't want him here now. So the imaging qualities now, as we're going to see later on, are much higher than that. Here, it's in an area, this is an IR millimeter image of that region. Here's Betelgeuse sitting over here. You see the belt stars around Nebula. Rigel's up where the N is here. And so it's a star forming region, 600 to 700 light years away. And this big thing here, which is called Barnard's bar or loop, is maybe due to a supernova explosion that took place in this inner part of the cluster. Okay, let's see. You saw my cat. So it's a very complex area and rich in star formation. It's one of the nearest star forming regions going. You notice Orion doesn't have as much gunk around it because it most likely moved from there to here. And some people claim that why it moved is that the supernova that made this ejected the star. So it was thrown out of its cradle. These are just pictures, quick pictures, radio image. The weird thing you're going to see here is with new equipment, you can do amazing work with getting one milliarcsecond resolution for things. And you see here, Betelgeuse is a radio source, and it's in there. Notice you see it's not symmetrical. There are like this bar reaching here. So it has like protrusions and prominence type things happen to it. And it's most likely due to the convection that's taking place in the star. Giant convection shoots stuff out. Another one is, the cat comes in the bottom now. The other one is a VLT optical image showing the star. Notice it's not quite symmetrical over here. There's a little protrusion, and these are the gases around the star. So it's not like the sun. It's not a spherical star. It has elongations due to probably gas being expelled in parts of it. It's not stable. So over here, you'll see this little thing where it's losing its spherical shape. Here is the star in an IR, a wide field IR image, with the Herschel telescope, 2016. What you're getting here is, here's the star in here. This is gas that's being ejected. And these are 3 ejections of gas that took place a while ago, speeding out at 67,000 miles an hour. And they're wondering what happens when these hit this so-called wall. So these are what are called bow-shocked features. And it's again because the star is moving fast. Another picture is another VLT image. These are the best pictures you get. Betelgeuse being so big, it's one of the few stars you can actually do surface features. So the star itself is that little dot in the center. They're using a coronagraph because it would blow out the detector to look around at the nebulosities around the star. You see these bright regions. And here's the picture of the star itself. And over here, well, I can't see, we'll see this one later. Another picture that's taken more recently. So the overall picture then, if you want to put it in our solar system, the star itself would go out to, around where Jupiter is. That's just blob. That's just stuck in there. And here you see the nebula and all that kind of stuff. And this bow shock, which you can see in here, is out to 30 AU. So the whole environment around the star is gaseous and nebula and dust, partly due or mostly due to the fact that the star is losing mass, ejecting mass or gas in gas cools and forms dust. I'm gonna have to get rid of this cat, I think. So he's helping, he's biting my hand. So here's the summary of the properties of the stars, and then we go on the second. So it's this 9th or 10th brightest star in the sky, and until recently it went from a 10th of magnitude to 1. This year in February it went to 1.6 magnitudes, which is the faintest it's ever been. Typically a spectral type is in here. This year it went to M4, which means it's about 3,500 degrees. That happened on the 20th. So this year it did many things that were unusual. It had it's dim. It got its temperature decreased, all that to values it never had. It's called a semi-regular variable, SG. These are red supergiants. There's abbreviation for that, RSG. It has 2 periods, although it's messy. It has like hundreds of periods, but the 2 main periods are 400 days and 500 years. Distance is hard to get. You think, easy star, right? Well, not. Hipparchus got a distance of 150 parsecs, 160, but it had a large error because the star is so bright. It was hard to, and it has a sun. It's not a, so it has a diameter, and trying to measure the parallax of motion of something that has size and it's first of all spotted and asymmetrical. It's hard to measure that. This measurement was made using the VLT and VLA radio measurements were made that pushed it out to 700 and something 24 light years or 222 parsecs. It was done with Harper. I was one of the collaborators on that. The temperature ranges between these values. The luminosity, 100,000 to 140,000. The luminosity of the sun. The radius is huge, 1,050. And that's because it has this diameter nearby. The mass is a little bit uncertain. It originally came from a star that was probably 20 to 22 solar masses, lost lots of mass in its 9 million years of life. They think it's down to 12, but they're still not uncertain. It could be 19, or it could be 10. And then its age is another thing that's not so certain. The latest paper on it gives it an age of 8.5 to 9 million years. This is where the fun comes in. The theoretical lifetime of a star of this original mass is that age. So Betelgeuse is nearing the end of its life. It's hard to tell exactly when that will occur. So its status is red. This is the status of the star. It's a red supergiant. SN2 progenitor is type 2 supernova, the ones where the core collapses. And you can compute how bright it would be because you know its distance and you know what these stars do when they blow up. It'd be about minus 10.5 to 11. That's about what the moon is. So it's going to be a pretty bright supernova whenever it happens. This is its evolution tracks, the simple one. Here's Betelgeuse and here's its twin Antares. It came across from here and went right across. There's Rigel. Went right across here. It's made a little glitch. So right across here, it doesn't do loops. Down here, stars do loops. So it just went right across and A supergiant, F supergiant, and now it's in the final stage where it looped up a bit. Here's a more professional looking one where my picture's blocking it out. But this is a luminosity and it's up where all the red supergiant stars are. This is a simplified version of that. So here it's born as a B009 star. It evolves to become a blue supergiant, yellow supergiant, then it expands out to be where it is now. And then unknown now, or if it blew up 724 years ago, it would be a supernova tonight. We just don't have much information upon where it's ready to go, but you have uncertainties in mass and things like that you can't pinpoint. You do know when it becomes a supernova that it will be bright because it's near us. It's only Antares is another supergiant progenitor. Antares, the red star there, and that would be brighter. But we don't. Antares seems to be a little bit younger than, and the choice is after the core implodes. If it's over 3 suns, 3.2 solar masses, it becomes a black hole. And if it's less than that, it becomes a neutron star. We think the star is down to about 12 solar masses. So we think the fate would be a neutron star. This is too technical maybe, but here is a HR diagram in log over log sun. This is the temperature, that's 10,000 degrees. That's 3,900. And here you see the track, it leaves the main sequence. The little glitch in here is when it starts, it's burning hydrogen. And there's a little glitch in here. You have helium burning and it runs across here pretty fast. And then up here. So down in here, it gives what's going on. Although this scale and the top scale don't quite agree. This is for a 15 solar mass star. So it's fully convective, the whole outer part of the star. Well, this is when it's an 009 to a B0 star. So it's burning hydrogen to helium in its core. It has, that goes on for about 12 million, in this model, 12 million years. And then it expands off the main sequence and becomes a red supergiant. This part in here refers to there. So you have then the core is now helium to carbon. There's convection going on there. There's a shell of hydrogen burning. As time proceeds, what happens in the center, the core, is that it gets so hot and so dense that the carbon fuses to oxygen, neon, magnesium, and eventually it's going to fuse to iron. The fusion to iron takes 1 day. Silicon to iron is 1 day. So that's what happens in the end of the star. It's still having shell burning. It still will have shells of surrounding it. It will have shells of helium and hydrogen burning going on before it blows. This is a good book that it's called Astrophysics of Red Supergiants. It's a good book to have if you want to go deeper in. So here's what it's, I said it was convecting. Over on this side is, well, that's supposed to be convecting. Over this side shows the granular, no, when I changed it to my wife's computer, I probably did not take that file with me. Okay, so this is a sunspot. These are granulations. See here, there's a little, and they change, they have lifetimes of 5 minutes. They're about 500 kilometers across. So the sun has these little convective bubbles that are coming out, and there's hundreds of thousands of them at one time on the sun's surface. Betelgeuse, the convection is scaled up immensely. We're on the sun, they're 500 kilometers, 300 miles. They have lifetimes of 5 minutes. On Betelgeuse, the models, and this is a model, it's not an artist, this is a model that people made of the star, is the whole surface is bubbling, and sometimes pieces of it, are dark, and sometimes it bulges out. And we think that in some ways this might be responsible, these convective cells, for the 300 to 400 day light variations that it has. It doesn't have a strict period. It isn't 330, sometimes it's 440, sometimes it's 380. We think it has to do with the lifetime of these convective cells. So when you have stuff rising up, it's bright, and when they fall, the blob falls back, and you have these dark areas. So this is going to count into understanding the star. These are models. People have been observing the star with interferometry for 20 years. This is a reconstructed image showing the convective cells on the star, 2013 to 18. Sometimes it gets dark because there's extra ones. I'm clicking the wrong button. And over here, there's a picture, an image of Betelgeuse with 2 bright spots on it, a little bulge area in here. So the surface is modeled with giant, bright, white, and cool areas, and it changes with time. This is this is done by IOTA in 2010, before the new devices came on, which skate circles around this. This has like a resolution of 5 milliarc seconds. The new instruments that you're going to see are 1 milliarc second. So this is the photometry part. This is the part that we're involved with. Photometry is, the study of the brightness of the star. It was Sir John Herschel, the son of Sir William, accidentally discovered that it was a variable star. And he took measurements of it from 1837 to 1851. We now have them, we got them from and archived in England. We didn't have them. Now we put them on a modern scale. And the star then was varying between 0.4 and 1.1 Mach. And there's continuous observations back in the 1880s, but not centered on the star. They were just made as part of catalogs. The concerted observations were made by amateurs, AAVSO members from 1920s to 2020. This is very compressed. You would see more action in here. Certainly you can see the 5-year period at times. 400-day period is harder to see, but when you do a escargot analysis of this data, you get a period of 506 days, although you see little periods around here. 388, this is 241 here, that 240-day one that I didn't show. So these aren't really periods, they're kind of cycles. They persist. And sometimes this 5.6 is now 6, so it changes with time. The cause of this 5-year one is maybe pulsation, and the cause of the 400-day one we call it is probably the lifetime of these blobs of hot material moving up, and making the star bright, and then as they cool, they fall down and it gets dark. It's not really known. Now for our data. This is analysis of our data. We took, we have 24 years of data that we took from, that Rick Wasatonic took from 1996 to the present time. This is better, superior. It's a photodiode data. You see, now you can definitely see the 400 and 20-day or so period in there. And you can see the evidences of this 6-year. Again, here, there's a dip. You can see the 6-year period. This is the analysis that we got now, of analyzing that data. And all these things above the false alarm probability of 0.0, all these periods are correct. You see here, this has, it likes periods of 400, 388, 470. So it kind of goes into, it's not strictly periodic. It kind of falls into times when the period, falls into those those holes. Now, looking at this data, this is kind of the best photometric data. It's done the V-band, and you just notice here that it varies. This is the year when the great dimming began. So right in here, as I'll show you later on, it never has begun lower than 1 magnitude. Right in here is where this triggered the release of this telegram. Used to call astronomers telegrams. And we call it the fainting of nearby red supergiant. And we just put this out. I put it out so that other astronomers would know it wasn't meant for a public thing, that, something strange is going on. It would be a good time to collect data with bigger telescopes. And it happened. Also, this telegram was viewed by a writer for National Geographic. So then it kind of went viral in the sense that this became a very newsworthy item in around Christmas time. So this is what happened. This shows the light curve from September, October. This is when we sent out the telegram. It was already down at 1.2 right here. So this is December 8th. And we thought, it was going to turn up. We thought, we didn't expect. So what you had there is you just had data to this point, and it kept going and going and going, and it reached. It was getting. We were afraid it was going to go all the way down, and then it would have been trouble. It bounced back up, and the last point, photoelectric point we have is at 0.4 magnitudes. That little X there is me going back to my amateur times. I did like an AAVSO member, I did visual estimates before when it was in here, and I correct it for the extinction. Now, all the comparison stars of Betelgeuse are higher than it. So when you just make a measurement relative to your comparison stars, its air mass is 2.2 at one point. So I correct it for the air mass, the extinction. And this is the last number that I got. It was 0.3, and then it's too close to the sun. So it vanishes from in this piece, this data in here, this black curve, is from the The black is by Don Corona. He's from Texas. You can, since the star is kind of a southern, it's 8 degrees above the equator. You get a longer observing season in Texas, even longer one in Hawaii. But we brought this fellow on, and he observed it, right to the bitter end. He did heroic measures to observe this, and he got the last. He was the last man standing, I said, and that's the last point. Now it's gone until the middle to the end of August, but you'll see at the end that it may not be gone. This Betelgeuse fell from number 9 or 10 earlier, and it dropped all these places. It fell out of the top 10, and then it was in the middle 20s. It was about the same, almost the same brightness of Bellatrix. It was really odd too. To look at Orion, you can notice it. It was dim. It was Bellatrix is 1.6, and typically Betelgeuse is a magnitude brighter. And we look at the constellation; it looked weird. So this telegram it began to get noticed. So this is I like all stars. So this is the pictures that some people took. I have them too, but these are better than mine. So here's Betelgeuse last year when it was 0.5 magnitudes. And this is a drop in magnitude. This is 1.5. So you can definitely, with your eye, you can easily see it, or with a photograph. Another one too, Betelgeuse when it was brighter. And then that was fainter. Actually fainter than that, but I mean, that was, you could see it. It was easily seen. It kind of looked weird to look at Orion and not see Betelgeuse being bright. So then all kinds of things happened for us. So flicker, orb of light, wonder if you still would. So it became supernova mania. We never said it was going to be a supernova. Will you immediately blow? Did you explode long ago? Flicker, orb of light. Well, we'll observe you ever. That kind of happened to me. I mean, I started, even though I did not think it was about to blow, I started going out even on cloudy nights with binoculars just to take a peek to see if it was still there, if it hadn't blown up. So I got sucked into the same thing, even though my scientific nature, there's a chance, who knows, 1,000,000 to 1 chance, 1,000 to 1 chance it was going to become a supernova, and I wanted to see it. And even though our equipment, we get cloudy nights here, even though we had 3 observers doing it, 1 in Oregon, 1 in Texas, you could have 2 or 3 days with no data. This is a Christmas card sent, New Year's card sent by a friend, and it says 1920, may you light up the dark. And so she has a picture of that. And so this is the kind of stuff that it got into the news. Even this was for sale. And it's a coat that you wear, and these light up, and actually Betelgeuse pulsates. I mean, I was thinking of buying that, but I'm glad I didn't. It's kind of cool to have that. It's so nerdish, and you could. The Betelgeuse was dimmable. They had a light on there. You could make an adjustment. So going back to the science, this is our data. It's being done with our work's being done with an 11-inch telescope. So it's 11 inches, and the observer is Rick Wastonik, a colleague of mine, and we're using specialized filters. These are called Robert Wing, called Wing filters, and they measure the TIO band. Here it is over here. TIO is over as being blocked. It's actually the TIO band's kind of big. It's all, this picture's blocked. So this would be another TIO. So we're measuring the height here and how far that band dips, because it's temperature dependent. So we have the V filter, because everybody uses the V filter. The V filter is a mess because it has all these bands of lines, titanium oxide, iron, and other titanium oxide. So it really doesn't give you the brightness of the star. It's kind of very dominated or contaminated by TIO bands. So these are the 3 filters, and they're cheap. We bought them for, I think they're by $50 each. And these are the band passes. And notice that one filter goes out to 10,000 angstroms. The photocell that's being used here is a solid state. So it has, it's a lower quantum efficiency, but Betelgeuse is really bright. But it goes out to 11,000 angstroms, which allows you to get the peak of Betelgeuse's emission is in this area around 9,050 to 10. It's where the maximum energy comes out. And it's a continuum, it's a line-free area. So how we measure it is TIO is this, we have two filters. We take the ratio of these two measurements, we form a TIO index. And then the C filter is in the area where it's very, very close to the maximum of the star. An M star maxes out around 1 micron, 10,000 angstroms. And this doesn't have any lines in it. It has very few lines. So this is a very, very close match for bolometric. So bolometric is how you can get luminosity. So it's a proxy for measuring. This is really cool. Using these three filters, a 10-inch telescope, we're able to do kind of neat things. Able to get the temperature of Betelgeuse or any red star, and able to get the bolometric magnitude. And if you know, of course, the distance, you can get luminosity. And here's the calibrations we have. This is TIO index running along here. This is stronger as you go out. And so this is a temperature calibration. We used supergiants and giants. Let me go back a step. And so this is how we worked it. We calibrated it using a bunch of M and K stars. We calibrated against spectral type down here. A TIO index of 1, which is what Betelgeuse achieved in February, was M4 star. It typically is M2 star. And the same thing, the temperature dropped to 35, 40 degrees Kelvin. So we're able to measure without having a large telescope using filters. We're able to measure by using the titanium bands, having this bolometric filter in. We're able to get all you need to get stellar temperature and luminosity and even radius. So this is the power of this. We're doing this for 25 years, 24 years. Power of this is having a continuous record and having these calibrations. We're able to use this small telescope, low quantum efficiency. Betelgeuse is the brightest, by the way, it's the brightest, except for the sun, it is the brightest infrared star in the sky. Its K magnitude is -4. So it's brighter than Venus. So it actually, in the 90s when I was observing this star, I got a message from a person using the secret space telescope, the one that was that the shuttle was built for, because they would roll they were looking for nuclear testing and things like that, and their calibration star was Betelgeuse. They rolled a telescope all over. It was made to point down. They rolled it up to get Betelgeuse in, and they were using it as a calibration. And in the IR region, it really doesn't vary much. I told them it was a variable star, and it is, but it only varies like 1/10 of a magnitude, and they didn't care. They sent me, the guy who was in charge of that sent me the data to be used on his death. I think he died. I never used it. So this is showing you what happens. This is the TIO band we use, and this shows you an M star has a TIO band, but it's not very strong, and it gets stronger with spectral type. So Betelgeuse went from an M2 star in here. What we're measuring is the drop of light, that versus that, and we have a correction from the slope here that we extrapolate down and take into account the fact that the continuum of the star is changing. We were going to put a filter in here, but then it was an extra filter, so we got away with cheating and taking this filter that was out here and getting the slope. And it's a minor correction. It's sort of 0.05. It's a 5% correction. So here you see how it works. So that's how these are all titanium isolate bands, and you can see what happens with the V band filter, which sits in here. It is a mess when you really are just measuring titanium oxide. This is a picture of just a titanium oxide. The red dots are just means. So 1, 2, 5. So this has a temperature of 3705. 75 is 36, and 1 is 35, 40. So this shows the variations of the star as it goes through these variations of 400 days. When a star is faint, the titanium oxide is strong, or what you would say cool. So we have very good data on that. This is what we did. This is our end result. That this is the V band, which is not usable because it's a filter that has very little astrophysical value, but it is the human eye. And so we always observed it because it was, people think in terms of the visual band. But more importantly, the TIO index and the C band filter were in here. So using the calibration, the temperature went from 36.42 in September to 35, 34 in February. And then the bolometric magnitude, the C band, changed by 70, well, and you put it into a non-log scale, it changed by about 30%. So here we have, so what we're using is this really high, very simple equation. Luminosity is 4 pi r squared, the radius of a star, times t to the 4th. That's sigma t to the 4th. And I left the sigma out. Sigma t to the 4th. So that's just the luminosity of the star. This is assuming it's a black body or a Planckian, which it isn't, but that's all you have here. So we computed, what would happen. We couldn't have the temperature drop explain what we were seeing here in the luminosity and in the luminosity change and in the drop of light over here. So we had to put in that we had to reduce the radius. So the star, we had it changing temperature, and then we could compensate for the dimness of it by having its radius change by 7%. The star's radius has changed by 20, by an amount, 7%, 10% in the past. But what we're going to see next is what happened. There was an image taken of, this is done with SPHERE. It's an interferometric 4 telescopes, the VLT in Chile. And they were able to image the star around this time. And this is the person that did it, my guard. I think I'm moving out of an exit point. So this is a picture of the star a year before. I notice it's not normal. I mean, it's not, it has, it's not a spherical body. And it had a bright area and then this halo around it. That's probably the upper portion of the star. But then this year, after the announcement was made, these people, Montardes et al., got discretionary time on the telescope, and they found this. So that data has not been published yet. They're still analyzing it because it's not as easy, the star sticking out over here. It's not as easy as it looks. I don't know if that's a way of saying it. So their explanation is that this is dust over here. This is a star ejected gas in our line of sight that has turned to dust. We think it might be a combination of one of these bright granules that's now sinking, or it could be both. So the jury is still out on this. I mean, this has happened 4 months ago. There are 4 groups working on this, and the results aren't published yet. I think he's having a lot of trouble analyzing this, and it's not an easy thing to analyze what caused this. In the IR, this isn't even here. If you go out in the IR, the star looks like that. So we think it's to be conservative. We think it could be explained by the temperature of the star dropping, and also there could be some dust in the line of sight. There are stars that have dust emission. These are carbon stars, though, our corona borealis stars. This is its light curve. These dips in here. This is 4 or 5 magnitudes. These things are, and they eject dust, and they the star dims 5 magnitudes. Only 1% of the light getting out. Those stars are carbon, and so when they eject the carbon gas, it goes out, and then solidifies into dust, causing it to block. So it's not unprecedented that this could happen with Betelgeuse. Okay, so let's get into the fun part, called the end of days. This is what happens when Betelgeuse becomes a supernova. So this is the story again, a B0 star, F supergiant, and then where it is now. And it becomes a supernova, a very bright one because it's nearby either a black hole or neutron star. Probably it's going to be a neutron star. More scientifically, this is a code run in 2016 showing the path. Here it is on the main sequence, and this is where it would be now. It's right here. And the circle in here is when it blows up. It's sort of, this is the uncertainty. This is where the star explodes. So it's within the errors. This is a fun thing. I learned a lot on supernova. I'm not an expert at supernova, but I was asked a lot of questions. So, and I had some friends who work in that area. So this is the internal structure of a supergiant on its last day. So what goes on is that you have hydrogen in the core. You start with hydrogen helium, and that burns out. You have helium to carbon, and then you have shell burning that we saw before. This core is very, very tiny. So this is the star. This core is somewhere on the vicinity of half the radius of the sun, but it has these shells that ignite. So, you know, hydrogen helium takes 7 million years, and then helium to carbon, another 7. It's done that already. And carbon to oxygen, things start to speed up. When it gets when it gets in here burning oxygen, the silicon is 6 months. Notice on its last day, it's forming the iron core. When the iron core forms, it runs out of nuclear fuel. Iron doesn't fuse or fizz very easily, and the weight, it has no nuclear reactions taking place, and it just implodes. And you have what going on? You have the iron undergoing inverse beta, the protons in the iron undergoing inverse beta decay, giving off neutrinos and neutrons. And that's going to be the formation of a neutron star. And that all happens in 1/4 of a second. So once the iron core forms, it's only a 1/4 of a second before things happen. The core implodes, and then it bounces back. Shock waves produced, and the shock wave propagates itself out through the center of the star. It takes hours for it to get out, and it's emitting gravity waves that get out right away, and it's emitting neutrinos. Neutrinos actually don't get out that fast. You think neutrinos go through anything, but you have very dense matter in there. So neutrinos that are produced interact with the very dense matter and actually power the supernova. 98% of the power of the supernova comes from neutrinos, which I never knew before. So that's its last day. And then I went into, so here's the core collapse. This is inverse beta decay. This is the core collapses and bounces out, and the neutrinos in there, it's called a proto-neutrino star, will oscillate. They produces gravity waves, and then the shock propagation goes out through the star. It takes about 3 hours for it to get from the center to the surface, because Betelgeuse is, it's out. The diameter is Jupiter's diameter, so it's going to take hours to get out there. And then you have what's called an amazing thing called the shock breakout. So the shock comes out here, heats up. The star's not a supernova yet, but the shock heats the outer parts of the star. It doesn't blow it up, it's just heating it. And then you get X-rays and gamma rays coming out. And then eventually you see some of that in light. This is called breakout. When this is something that people do with atomic bomb tests. They look for the breakout before, well, the supernova is when the star explodes. The breakout is when it reaches the surface and heats the surface up. And then briefly after that, the star explodes when you get the supernova. So that's what it says here. gravity waves from the core, and they get right out. The neutrinos are delayed a bit, but they go out right afterwards. So one of the things that happens, they have what's called they have a network, SNOOS. It's a supernova alert network where they have neutrino telescopes, because you get to see the neutrinos coming first. And probably in the case of Betelgeuse, because it's a big star, about 3 hours later, you would see the supernova itself, the start of the supernova event. In 1987, we had one neutrino detector. It detected 24 neutrinos coming from supernova 1987A, and the one in the Large Magellanic Cloud. Betelgeuse being much nearer than that, that was 160 million light years away. Betelgeuse is 20, the supernova in 187A in LMC was 160,000 light years. Betelgeuse is only 700. So they estimate that 25 million neutrinos will be detected. So it will be easy to find it. This network's set up for detecting supernova in our galaxy. And what they want to do here, they see the neutrinos come out, and then you can point your optical telescopes to that galaxy to see, or our own galaxy to see the event. Now, the shock breakout has never been observed. This is when the surface heats. The star has not expanded yet, and it's predicted, and it has been observed. So the bottom line here is the surface expands in supernova. That gives you the bright star. It's expected with Betelgeuse to be minus 10.5 to 11. The full moon is minus 11.15. So actually, almost 10 years ago, the breakout was observed by the Kepler satellite. Kepler was pointing or staring in the direction of Cygnus and Lyrae, and it detected, this is its light curve, it detected this little blip here, and here's the shock breakout. It's never been observed. This was kept quiet for about a year because it's important to notice in nuclear bomb tests. This is one of the things they look at before you see this explosion of gamma rays and all that come for you before you see the explosion. So here you have the star, the breakout, and then you have the star expanding, brightening, and you get maximum brightness in 2 weeks. The breakout lasts about 20 minutes. So this was observed by satellite, and it turns out that there was this man, an amateur astronomer, who contacted me when I was in the news. His name is Uso, he's right here. He has a 16-inch telescope, and he was doing testing. He just got a new camera, and he was testing, taking pictures of NGC 611. And he noticed that something was just blocked out. He noticed that there was a star here that was brightening, and that had dimmed. So he was the only person in the world that saw this in real time, this shock event. It's kind of cool. He wasn't looking for it. He just happened. And what happened is that he developed the plates. Most of the time, well, it wasn't plates, it was a CCD. And so you see it brightening, and it would dip. It dimmed, because that's what they do. This lasted a total of 30 minutes. So that's when, before the supernova began, when the surface was heated by the shock, this event happens. So now the supernova early warning system, I joined this. I didn't know anything about it until I was working on Betelgeuse. And I wanted to know if it was going to blow up, even though scientifically I thought it shouldn't blow up, but you know why, you never know. So they have a network of neutrino telescopes in the US, and one in Italy, and India doesn't show up, but there is one there, in the Antarctic. And these are going all the time, and they have a system where if a surge of neutrinos comes in, they can give you the direction if two of them are working and count. So I joined this. It's easy to join. It's going to click and you put your email in. And that gives you 2 to 3 hours warning. I also, because of Villanova, Amber Stuver is there. She's a member of the LIGO group. And I asked if I could, because they have an alert system too, mainly for gravitational wave, the merger of a black hole and a neutron, article, I asked her if I could join that alert LIGO because it would come a little bit sooner than the neutrinos would. So no, I got nothing. But one night, well, I wasn't even. I didn't even get the alert. But I got the alert, but it was like it was old. So this got my attention. And January 13th, January 15th, sorry, 2020, they put out an alert, burst of gravitational waves detected coming from Orion. They have Betelgeuse here. This became a big deal because it was all, the height that Betelgeuse was about to explode. So I saw this at, 2 in the morning. I was going through my emails. I guess I couldn't sleep. And I ran outside to see if it had blown up because I saw this report a few hours late. Lo and behold, it was still there. So I was getting into the supernova mania. So this is what it would look like. This is a winter scene. This is the Betelgeuse now. And there's Rigel and all the stars, Betelgeuse and the cult stars. This is how it would look. So it would be pretty bright. And notice when I photoshopped this, the shadows are facing the wrong way. So let's go back and look at how it would compare with other supernova, other bright supernova. In our galaxy, we should have 2 to 3 going off every 100 years. In the universe, you have one happening every 3 seconds. So, and you know that supernova type 1A are distance indicators. So there's teams that have round-the-clock observations searching for supernovae. They don't go unnoticed anymore. So you might have 100 of them, 50 to 100 detected in one year, not in our galaxy, but elsewhere. So I just want to get into these last ones. Let's take the last 1,000 years. This is the Crab Nebula that took supernova. It's not the Crab Nebula, it's wrong. That's not the Crab Nebula. The Crab Nebula was 1054. This is screwed up. I just noticed it now. So we'll go over the supernova 1006, 1054, and Tycho. And the last one was Kepler supernova. So what's left here is the remnants. This is the remnant of the explosion. Expanded it up pretty far. Going back and looking at how they measure the brightness is estimated that the magnitude for this was minus 7.5. That's pretty bright. That would be visible during the day. And it was seen by Chinese and Arabic astronomers, but it was not reported in Europe. It's in the constellation Lupus. And they reported, the Chinese astronomers reported that it cast shadows and at night, and it could be seen. So that's like 4 or 5 times brighter than Venus. So it could be seen in the day. The estimated brightness, this is a type 1 supernova. This is a merger of a white dwarf gaining mass and exploding. Was about minus 19.4. So they even have like what it's 7,000 light years away. So now it has a number because it's a radio source. So that would be pretty bright. And so that was 1,000 years ago. The one that's most famous is this one, supernova 1054. It was observed July 4th. There's a lot of records on this. It was visible in the daytime and it reached minus 6. So today, the remnant of this is the Crab Nebula, which in the center of that, somewhere in there, is a neutron star. Here's a picture of the Crab Nebula taken in different wavelengths, from IR to X-ray to gamma ray. It has different shapes because of the way the shock fronts are heating. So as the gas expands, it runs into the surrounding gas and gives you these weird, this is the light one. So they just made a composite of 6 or 7 wavelengths and combined them into one image. Kind of cool. This one maybe was seen by the North American Native Americans in this picture here. The Crab Nebula, or the supernova 1054, took place in Taurus. And So, and they went back and here's the nebula in here. And they computed where the moon would be on the night the crescent moon was supposedly. I don't really trust this, but some people do. And I guess that's the guy's handprint. The second most recent one, and we're being cheated because they should be going off every year, every 100 years, and they haven't been. Is supernova 1572 called Tycho Brahe's supernova, even though he didn't discover it. And in those days, in 1572, they had a map of it. It took place in Cas. This is known as Cas A now. And they could determine the magnitude of the star by comparing it to other stars in the field. And Venus happened to be nearby, and Venus was -4. So they were able to put a pretty tight magnitude on it. That's the remnant of it. Of course, we can't see it now, but that was well observed. This is Tycho now. This is a supernova image. When they explode, they very high speed. You're going like half the speed of light. This stuff runs into other gas around it. Because these stars were red supergiants at one time. We know how messy it is around Betelgeuse. The shock, the star exploding envelope of the star hits the shock fronts, produces all these heated compressed gas regions. I know you can see all this, but they were able to, they went back in time and they did measure, now we're 1572, they were able to measure the reconstructed history of the star by comparing it to, it was brighter than this or fainter than that. And they were able to make a so-called light curve. They even got it before it went, they got measurements in reconstructing this, that it was fainter than a fifth magnitude when it started. It's kind of cool. I didn't know people did that. And here's the last supernova, bright supernova, to be a galactic supernova. And it was called Kepler's supernova. So it's called the last bright one. It took place, it wasn't all that bright, it was -2.5. And it took place on 1604. This is they had sketches of this at the time, people sketched this. And so they placed it, Mars and Jupiter and Saturn all there, and it fits in very nicely. This is that's the remnant today. Supernova, Kepler supernova was a type 1, where you have a big star dumping gas onto a white dwarf. The white dwarf reaches 1.4 solar masses and just explodes. There's no remnant. There's no neutron star, no black hole. It just detonates in a very energetic explosion. So it's thermonuclear. And so it's a different type of supernova. And here's the light curve. Again, people went back over time, over historical data sites in Korea and Europe, and reconstructed what the light curve was. That's how they could tell it was a type 1A supernova rather than the type 2. And the last one, the last bright supernova that, visual, I saw this one, I was lucky. I was down in Argentina. It took place in a Large Magellanic Cloud, February 1987. I was down there for some reason, Halley's Comet cruise or something or other. And so, it isn't spectacular, but this is the star was 15th magnitude. And then during maximum brightness, it was 3.2. I would be happy to see another one of these. And this made Time magazine for that year. So again, to end this part, Betelgeuse now, Rigel now, this is Betelgeuse when it blows up. And then I looked into the remnant of Betelgeuse, and it would probably resemble the Crab, because the Crab Nebula has a lot of nebulosities around it. And this would probably be visible and discernible, probably a little bit fainter than I couldn't dim that too much, about 50 years after it blows up. Here's the Orion Nebula, and it would outshine the Orion Nebula by 10 times. So that's what you would see in place of it. Again, you have to dim that down a little bit. I didn't try to dim it. I couldn't figure it out. So getting to the end, something happened. I told you Betelgeuse goes out of view from the Earth from May until August. And I got an email message from a amateur astronomer from Texas And he said, could you observe the star from Mars? And I said, maybe you could. So then I was interviewed by a reporter who happened to know the people who ran the Mars rover camera. His name was Mark Lemon. So I got my courage up because I didn't want him to laugh at me. I sent an email to him. I know this is a silly request, but Betelgeuse is out of view for 3 months. It's doing strange things. And we're wondering if we could get an observation of it from Mars. And so he said yes. And they observed it today, actually. I don't know what happened. So using the Mars rover, this is the Curiosity, it has 2 CCD cameras on. Here they are. 2 CCD cameras, a wide field and a high resolution and a lower resolution camera, are equipped with filters. The ones that you use, the B, G, and R filters, so you can combine them and make color pictures. That's what they do here. I was using a filterless system would be kind of rough observing, getting the magnitude of Betelgeuse because it's such a red star. And I was also nervous that these didn't have the IR filters. These detectors let a lot of IR light in. So they have an IR blocking filter, which is otherwise the observations would have been useless. So he wrote back that that filter is there, it's IR blocked, and they are willing to do it. I think it's fun for them. So today they did it's always strange. I didn't know exactly where. I had to figure out whether you could see it from Mars. And it's not the best time. It comes up in the morning. A month from now is better. But the Martian atmosphere, you see this color here? The Martian atmosphere is like having smog. The dust forms, and the extinction is the same. Like on the Earth, the extinction in blue is 0.3 magnitudes, and yellow 0.2, and so on. Ultraviolet 0.5. Here you get like the same extinction, because it's really the extinction is caused by the dust particles in the atmosphere. The atmosphere itself does nothing. It doesn't absorb any of that light. And this time of the year is when they start getting dust storms. So I went through the literature and I found out that actually there was an image. I mean, this is what got me onto it. I was trying to find whether they did it before. And they have a picture of the Earth, and they have a comet, I think they did. So this is the rover Spirit on March 11th, has a picture of Betelgeuse here. Here are the belt stars, and here's Bellatrix. I think that's a cosmic ray. To do it correctly, this is a blue star, it's a red star. You have big calibration problems in getting to the V system. This star here is a G8 star, so it's closer in color. We use this guy because it's nearer to the extinction questions. It's so big, it's closer in color. Bellatrix is so blue, it would be far away. So you do have to worry about extinction like you do here. When you do variable star observing, you want your comparison star to be nearby, and you want it to be about the same brightness, and you want it to be the same color. So they did have this picture. This isn't a usable picture. I was trying to figure out. I tried to get the magnitude from this, and I did, but I knew, for example, on that day it was 0.52 because we have observations going back to 1994. And I couldn't get anywhere with it. So today they did a test of the atmosphere brightness and how bright the sky would be, because it rises in twilight, Betelgeuse, and I think it goes into the sun. It's just coming out of the sun now. So I don't know. I never thought they would do it in June. I thought it was going to be. They said they would do it, but I thought it would be July. So I'm very happy with it, and it would be kind of fun observing Betelgeuse from Mars. It's astronomy from Mars. That ties into my other project. So anyway, see what happens. I know they observed it today as a test, but I think they were just observing just the sky brightnesses in the extinction. The trouble may be is that the spring, this is spring on Mars, and then the northern hemisphere, and this is when they get their dust storms. So big dust storm happens, it's over. So thank you. Hopefully you'll see this. It won't be that bright. You'll see this. You'll see a supernova in your lifetime. It should go in the next 10,000 years to 50,000 years. It could be any time from now. I have, I'm 75. I don't have many years left. You have longer time. I don't think it will go unless the summer, when they look at it, they find it to be, has gotten 0 magnitude or something. So it's fun. I'll be working with it. I want to tell you too, we've been observing the star for 25 years, and it got to be boring. And Rick and I last year said, in the beginning of the year, no, this isn't doing much. We have 24 years of data. We can get the periods out of it and all that kind of stuff to determine the convection zone cycles. And we almost stopped observing it, and fortunately we didn't. Okay, thank you.
Great job.
Thank you. Thanks, Ed. I'm reminded of a Bad Company that used to sing, "Don't you know that you are a shooting star?" We need to change those lyrics to "Don't you know that you're a type 1A supernova?"
Yeah.
I also draw inspiration from the fact that you talked about heroic measures and last man standing. And we are astronomers. So that works.
You know how that is.
Definitely works for me. Thank you very much.
Well, I do that too. I mean, I observed the star in May 10th, to the last point, and it was trouble. I was out. Yeah. The corrections got to be so large in extinction, and I didn't have any. I wasn't sure whether it was right. If you have any questions, I'll be happy to answer them.
Yeah, I'm going to look in the chat. If you've got a question, post to the chat or raise your hand, and we'll call on you. And Ed, if you could stop sharing your screen, we'll be able to see more folks.
Yes, let me stop sharing. Stop share. There we go.
There we go. If you've got a question, post to the chat or raise your hand, and we'll call on you. And Ed, if you could stop sharing your screen, we'll be able to.
I thought stop sharing my screen altogether.
Somebody's got an echo.
Yeah, it's me. I'll take care of it. There we go. Somebody's also listening to the YouTube.
Oh yeah, there is a delay in that.
Yeah.
Like 20 seconds. Oh, stop sharing my screen.
Okay.
Okay, I think I got it.
I have stopped sharing my screen.
Okay, good. So let's see. Lou has a question. Louis, go ahead.
Sure. I just want to know, 25 years or 24 years is just an amazing, amazing stint, and kudos to you. Brilliant work. Do you know of any other observing programs of any scale of Betelgeuse or something?
No, well, the DVAA VSO has been doing it since 1920s, but they're visual estimates, and there's a few other stars. I started doing it, and then I got hooked. I said I wanted to get a nice data set so I could pull out those periods. That's why I was doing it. And,
dare I ask, are there any other observing programs that you've been involved in for anything close to this amount of time?
Yes, there have been. I mean, I get crazy on things. Beta Lyrae, Myra. I have 10 years of Myra data. You can't really know much about a star in a year. You have to stick to it. And there were things I did for five years. I just learned that observing a star for a week isn't going to give you much. But if you're looking, yes, let me go back. There is a system now. We're doing Cepheids. Scott Engel and I at Villanova, back in hundreds of years of historical data, because these were observed, they were discovered back in the late 1700s, 1800s. And by having, this is like 200 years of data, Cepheids have big light variations. We observed times of maximum light. We were able to get those back 200 years. and you can actually see them evolving. You know, you can't see the star change as the Cepheid ages. It gets bigger, and bigger means the period will get longer. So we've observed period increases for about half of the stars. Polaris has that data. Delta Cepheid. It wasn't only our data. We just used, you know, why wait 50 years in the future when you have a data set that's 100 years and pretty good data, and 200 years in one case. Delta Cepheid goes back 250 years. And by using that historical data, we're able to actually check on the evolution of the star, you know, one of the stars. So historical data is kind of neat to have. People are using it now. I was in the beginning, I used it years ago. I like going back. I went back and looked at Betelgeuse to see what the Persian astronomers measured. And first magnitude star, you're not going to get much out of it. And we did this with Polaris itself. Polaris is a second magnitude star. Back in the Almagest and in the fixed stars by the Persian astronomers, it was listed as a third magnitude star. So, no, we thought that might be real. It's the only star we saw that did that kind of change, that changed by magnitude.
Wow.
You know, so old data is a gold mine. I had to go. I went to Iran to actually find the book. It was published in 962, and I had copies of it, but I didn't have the original. The original was in Mashhad, the holy city where Imam Reza is buried, and I had to kind of go through the ritual of converting and getting in to see the book. And the book was just sitting there. I said, "Do I want should I put gloves on?" No, just look at it and copy it, take photographs. I was amazed that it wasn't really kept in a vault or something like that. And I did, while I was there, I did look at Betelgeuse to see what he had given for its color. There's a controversy that Betelgeuse was yellow, and then in some books it's red or orange. I mean, and yellow would mean it went through the yellow supergiant phase much faster than we expected. So yeah, you get a lot out of continuing long-term observations. Not many people do it because you get time on large telescopes. It's for a night or an hour. So Rick we had our own telescope. We didn't have to apply for time. It's an 11-inch telescope, and so we did bright stars. So we're continuing to do. Maybe you're sitting on 10 bright stars. Rigel, Myra, the name stars, and we've been doing continuously in the same system, and that's very useful. You don't have to combine data sets. You get into trouble when you do that. Thank you for the question.
There was another question that I'm going to modify slightly. Why is it difficult to pinpoint the time of a supernova? Not enough data or computational limitations? And I'm going to add, or something else.
Pinpoint the time. Well, you're not looking. You only notice it when it becomes a supernova. So you're looking at the whole. You're not looking at the whole sky. So supernovae are not identified until they're like a quarter of the way to maximum brightness. So that's why you can't sit on a star and just wait. Mm-hmm. So that's the reason. And the only reason that the burst in the breakout was observed is that the Kepler satellite pointed in an area where there's lots of galaxies and possible supernova, and they were observing 150,000 stars. So one of them went. Right. So that's the breakout was the holy grail, observing a supernova, that you would get it as it. That's not the supernova itself. That's the shock. The supernova is when that whole star blows up. That's when it's really bright. Yeah, it was neat. And for that amateur astronomer contacted me I guess in January or February. I wasn't aware of his work. I'm not a supernova person, so I was getting questions on supernova all the time, and I had to consult with friends of mine to explain it to me. And there was one paper, his name is Mark Fuller, a supernova expert, who said that in his models, stars supernova fade in visual about a magnitude before they blow up. And he, that caught my attention too. He said at the end of his email, I don't think it's going to happen, but don't blink. So I was getting into even though I did not think of this as an imminent supernova, I started to go out at night and look, in the cloudy nights, and we couldn't observe it, just to make sure it was still there. Part of the cloudy nights, you can see if you see the star. It was
Michael,
it was fun.
Michael, you had a question.
Yes, I am off mute. My question was, one of the early slides in your presentation, it showed the proper motion of the foreground stars compared to the belt stars of Orion. I was wondering what software package was used to show that proper motion.
It's not mine. I got it from the web. I think it was done at Hayden Planetarium.
Okay.
Yeah, it probably wouldn't be hard to do with Gaia data. You could probably make animation like that. I wasn't about to do that. I did work on in 2007 with its proper motion and radial velocity to try to trace it back to where it was formed, and we couldn't get it to match because at that time we were using the Hipparchus parallax, which is 160 parsecs, and now when you're using 220 parsecs, if it's really at 250 parsecs, it goes back. It traces back with radial velocity and proper motion to the OB1 Orion group. So, and there's a theory that Betelgeuse is not a normal star, that it merged with another star, and also they think, or the other idea is that it was in a binary system where the star underwent a supernova, and that's the Barnard loop, you see, and that seems to be centered on the Orion OB region. It's really hard, if it got ejected at a million years, you have encounters with other stars, and they're not straight line paths. You can't trace it back. The galactic models, we were trying that. You have to get it when you go for a million. It's like when these extragalactic comets were coming in, that you could track it back to the star where they were formed. It's really hard to do that. That's with the Gaia data and better galactic gravity models, you might be able to. We didn't want to spend a lot of time on it. We put it. I did that work the lead author was a friend of mine, Ben Harper. We were more interested in refining the parallax. But then in doing that, we decided, let's try to trace it back, see where the thing was, where it originated from. It's moving fast. All those other stars in Orion have motions of like 5. That Orion is like 30 something. It definitely has different motions than the rest of the stars. And in fact, it doesn't have, all young stars are born in groups and associations, OB, and Orion doesn't have it. So that means to me that it was ejected from one. The nearest case is OB1, the Orion belt stars. That's the direction it's coming from. Anyway, yeah.
Thank you.
Any other questions? It was a very thorough presentation. That's why there was no questions.
Maybe it was too thorough. I don't know.
No, not at all.
I'm giving a technical talk in Vienna, so in 2 weeks. So I was going to do the Mars, one, because I have that done. This one, I finished it today. So it's never been given before. It hasn't been polished that much.
Are you going to do it live in Vienna?
No, I'm going Zoom.
Okay.
I was supposed to give it live. I accepted this talk because I wanted to go to the, and no, I just not quite the same. So then I have to worry about the people working on the star. Some of the people will be tuned in. But it's kind of gotten competitive on what happened coming out when people. See, I believe that it was a combination of dust and the temperature drop. There's another group saying it was just the dust. Out of that, I don't know why the dust would happen every 400 years. So we have different competitors of sorts, and these are the guys with the big telescopes, the VLT, space telescope. So we're kind of well, what we're getting out of an 11-inch telescope is being pitted against people who have using much larger scopes, and so you're trying to hold your own there. I'm the star, and I've been observing it for longer than sometimes before some of my competitors were born. So I know the star. Back in the 80s, I've been observing it, so I know the star pretty well. I got to know supernova well this time. Well, I teach supernova, but it isn't one of my areas. And so you learn a lot. The star has every aspect going for it. Evolution, supernova, nuclear physics, all kinds of things. Stellar structure, gravitation. It probably has magnetic fields. There's one group that thinks that spot is a magnetic, like the sun, giant sunspot. So none of these groups have published, because I think they're all having the same problems I'm having, is trying to get it all to fit in one model. And I don't know. They're not talking. I have email conversations, and now I no longer have them because they consider me a competitor. We're publishing our paper in about 3 weeks. I would love to know what other people got before I publish it.
Somebody else asked, you mentioned motion of Betelgeuse. What motion of Betelgeuse is what kind of motion is Betelgeuse engaged in when you say it moves fast?
Oh, it's going at 67,000 miles an hour. That's 30 kilometers per second. Most stars in that area of Orion are going like 5 or 6 kilometers. So it's going faster than the younger stars. So that's what I mean. And if you put the whole motion into 3D motion using proper motions, RA and DEC proper motion, you can get what's called a space motion. It's kind of large for a young star. Young stars have space motions similar to the sun. This doesn't. This has larger space motions, and it shouldn't, because this star is young and it's only 10 million years old. So and in fact, it doesn't have any companions. It's not in a it's not in a cluster. It's not a binary. All these things are pointing to the fact that it's been ejected from a stellar group. And I'm pretty sure that's right. I've never seen a supergiant. All supergiants they're young. They're 10 million, 20 million years old, and they're still associated with where they were formed and with stars around them. This star isn't. The age is pretty well determined because of using evolution codes. They all kind of agree between 8 and 10 million. If the mass was known better, then you could pinpoint when it would become a supernova. The mass is still not well determined. There's a lot. You need a lot of the trouble. Even when we did the distance, we used a VLA radio. We got a radio parallax, combined it with the light. We still have an error of 20% in the parallax. If you use Gaia, your error is 1%. So if this star were fainter, we were looking for a companion. We searched for companions with Gaia. We took the Gaia field and went 4 degrees around Orion, around Betelgeuse, seeing if we could find a star that had the same proper motions and radial velocities. There weren't any. So if you found a companion, it would be fabulous, because then you could get the distance from Gaia. Gaia has great distances, but it can't do below brighter than about 6th or 5th magnitude. We did this with Polaris. Polaris's distance was kind of screwed up, and we got Gaia has a 6th magnitude companion, and Gaia measured its parallax to plus or minus 1 parsec, or 3 light years, and so we adopted that. Polaris's distance is now very well known. So if we were hunting around for, it turns out that Rigel has a companion, so you can use that to get a good distance. And we just got one for Antares, which is the twin to Betelgeuse, and it has a companion, and it's in a cluster, so we got its distance nailed. Hipparchus, where the parallaxes are coming from, does not do a good job with bright stars, and especially if they have diameter. These stars don't, because you're measuring parallaxes from the centroid of light. When the centroid of light is not the center of the star, or if it varies, that throws off your measures. So if you can get a companion star near it, not too near, but 10 arc seconds, then you can nail the distance to a couple parsecs. That would make a big difference with Betelgeuse if you could do that, because then you would, its precise distance, and then you could put it into, its absolute magnitude or luminosity, its radius, better than what you know now. That's why the uncertainty of when it's going to blow up, I think it's more uncertain than, it could have blown up already. That's how uncertain it is. We know it hasn't done, well, it has 700 years to get the light to reach us. It's just the uncertainties in its physical parameters are still not good enough to pinpoint when the star will blow up. So just watch.
Great. Any other questions? I don't see any in the chat, and we're close to our witching hour.
Yeah, I see you still have 27 people. My God, that's good. You had 30,
yeah.
You had 33. That's good.
You've done good.
Done good.
Jeremy, you want to tell us about our next meeting is July 10th. Jeremy, you want to tell us about that?
Yeah, so on July 10th, we'll have, as I said before, we'll have John Sickle, who's a professor of music at Raritan Valley Community College, and he'll tell us about musical soundtracks in space.
Like that.
I'm looking forward
to that one.
Something more attuned to my liberal arts background. Looking forward to that. Well, Ed, thanks once again. Good luck with the presentation in Vienna. You're welcome to join us. What typically happens after our meetings is we retreat to Manila's diner, mainline diner, on Lancaster Pike. I don't think they're allowing indoor seating quite yet, even though we just turned yellow. So we'll just remain, those who would like to are welcome to remain here on Zoom and hang out for a little while longer if you like, and you're welcome to join us. Thank you.
Okay, thank you. I have to give my computer back to my wife.
Yeah, I understand. And those who don't want to hang out, we will see you July 10th, probably still back here. If there's any change, watch the listserv if there's any change. But otherwise, we will probably continue to meet virtually until there are no restrictions on public meetings of greater than 25, because we generally get 40 or 50 at a meeting. And the other possibility that the Zoom meetings provide us that I'm still exploring are getting guests from further and further away who might not come to a Friday night in Radnor, but would be more than happy to hop onto a Zoom meeting. So stay tuned for that. And if you have any ideas of guests like that, please let me know so we can extend an invitation. And that would conclude the general meeting. The party's on.
All right. Yeah, I stopped the recording and I will shut down the YouTube stream now.